We were looking at what happens when you use differentiation from first principles to differentiate some simple functions. Let's summarize what we found. We found that when y was x squared, then we found that the derivative, the differentiated function, which we decided to write as dy dx, is 2x. And this shows us the gradient of the function. What do we mean by the gradient to a curve? We mean that if we were to arrange a straight line that just touched that curve at a particular point, this would be the gradient of that straight line. And of course, because it's a curve, that straight line will be different depending on which point we touch it against. So therefore, the gradient won't just be a number, it will be a function that depends on the x-coordinate of the point we're interested in. We also use differentiation from first principles to differentiate x cubed, and when we did that, we found that the differentiated function was 3x squared. We didn't do y equals x to the 4 from first principles, but it wouldn't have been substantially difficult or different from what we did to do that. What we would discover had we done that dy dx would be 4x cubed. Now, this is starting to look like there is a pattern going on. What would the pattern suggest if we had y is x to the power of n, where n is any positive integer? That would suggest, looking at these previous results, well, when we had x to the 2x squared, we had 2 lots of something. When we had x cubed, it differentiated to 3 lots of something. X to the power 4 differentiated to 4 lots of something. So it would seem a reasonable assumption to say that if you differentiate x to the power of n, you will end up with n lots of something. What about the rest of it? Well, when we had x squared, it differentiated to x, or x to the 1 if you like. When we had x cubed, it differentiated to a certain amount of x squareds. X to the 4 differentiated to a certain amount of x cubed. In other words, this power is 1 less than the power of x in the original function. So that would suggest that we would have x to the power of n subtract 1. And indeed, this is the general rule. We haven't proved that, we've given some suggestive evidence, but you will not have to prove it for most courses of an elementary nature. You'll just have to know it and be able to use it. So now that we do know it, let's just look at a couple of examples. Suppose that we had to differentiate y is x to the 8. Well, we now know then that dy dx, the gradient of that curve, will be 8x to the 7. Similarly, we could do this with silly numbers now. Suppose we had x to the million. We could now tell that dy dx would be 1 million x's to the 999,999. You're very unlikely to see examples like that, but the rule is exactly the same for every positive integer value of n. Now, we can therefore differentiate any power of x, but that's a very restricted and simple class of functions. How about something a bit more general? Suppose we had not just a power of x, but a certain number of them. I mean, suppose we had 4 lots of x cubed, and I wanted to differentiate that. Well, thankfully, this is as simple as it could possibly be. Take the 4, hive it off, stick it in a bracket and ignore it for the moment. Now differentiate x cubed in the way that we've been doing it up to now, giving us 3x squared. Well, dy dx is now these two things multiplied together. So 4 times 3 is 12, so it's 12 lots of x squared. Haven't proved that this is a rule. Again, that's not tremendously difficult, but proofs are usually unnecessary for the level that we're looking at. So let's write that up as a general rule and do a couple more examples. What we have said there, therefore, is that if you have got a y which is a certain constant k times x to the power of n, then it follows that the differentiated version of that function, the gradient function dy dx, is k multiplied by n multiplied by x to the n minus 1. Let's just put that into practice. So suppose we have 7 lots of x to the 5. Then this would suggest that dy dx is going to be 7 lots of 5 times x to the 4. In other words, that dy dx is going to be whatever 7 5s are times x to the 4. One more example. Suppose we have a y which is negative 3 lots of x to the 6. This suggests then, using the rule, the gradient function dy dx is negative 3 times 6 times x to the 5. So what is negative 3 times 6? It's negative 18. And we get negative 18 x to the 5s. There is no need for this k number on the beginning to be positive. It could be absolutely anything, positive, negative, doesn't even have to be a whole number. Fractions or other numbers would work absolutely fine. So we can now differentiate anything that looks like this, anything which is a certain number of x to the n's multiplied by some constant. Now there are a couple of special cases that are worth understanding and knowing about. Let's start off with this special case. Suppose we just had y is x. Well, if we were to follow the rule to differentiate that, that would suggest that what we get is, oh wait a minute, what power of x is this? Well, x is just x to the power 1. So the rule would suggest that the 1 comes down the outside, and this becomes x to the 0. Now what is x to the 0? Well, there is a very good argument that suggests that anything to the power of 0, well, almost anything, is 1. So that is going to be 1. Now I'm not going to prove right now that x to the 0 is 1. There's an interesting video I can point you in the direction of if you are interested in that. For the moment I ask you to take that on trust. So that means that the dy dx in this case is just 1. Well, that's just a number. I thought we said we were going to get functions rather than numbers. Well, if you think about what this original thing is, it is a straight line with a gradient of 1. So this makes perfect sense that we would get that. And in particular now, what about a general case? What about something like y is 3x? Well, follow the rules of differentiation. We said on the previous page, if you've got a number times a thing, then take that number, stick it in a bracket, worry about it later. Just differentiate the rest of it. We've just said, when you differentiate x, you get 1. In other words, the answer to the differentiated function, the gradient function, is 3. Well, I certainly hope you would agree with me that 3 is the gradient of this straight line. So we've got another general rule which says that if y is some number of x's where k is just a constant, that means that when you differentiate it, you just get that constant. Final special case. What if we just had y is a number, like y is 6? Well, think about what the graph of that will look like. If that's your origin on an x, y graph, then if this is the line y equals 6, how steep is that line? What is its gradient? Well, it's parallel to the x-axis. Its gradient is 0. That means, therefore, that dy dx in this case is 0. And in fact, it didn't have to be the line y equals 6. It could have been y equals any number. So here's our final special case. If y is just a number, then that means that when you differentiate it, you will always get 0. Let's just summarize all the things that we've looked at in this video. Firstly, we had a general rule that said that if y is some positive integer power of x, then when you differentiated it, you got n x to the n minus 1. We then extended that very slightly to to say that suppose it was some number of x to the n's, not necessarily just a single x to the n, then that rule was not much different. This was k times n times x to the n minus 1. And you can possibly see that the first of these rules is actually contained in the second one. It's a special case where k equals 1. We also found that if y is k times x, just x on its own, in other words this is the equation of the straight line, then when you differentiate that function you just get k, which makes perfect sense if we want to talk about differentiation and dy dx to be the gradient of the function. And the final one we saw was that if y was just a number, in other words if you're dealing with a horizontal line, then when you differentiate that you will get 0, because the gradient of a horizontal line is 0.